Now we'll turn our attention to alcohols. Remember, they have the functional group of OH. In terms of their general formula, it's CnH2n plus 1 OH. That functional group is there. Now, the OH group in alcohols means that hydrogen bonding occurs between molecules. Remember, hydrogen bonding occurs between hydrogen and a highly electronegative element, such as oxygen. Alcohols therefore have higher melting and boiling points than alkanes of similar relative molecular mass, because hydrogen bonds, remember, are stronger than London forces, van der Waals forces. Short chain alcohols are soluble in water, again due to the presence of that hydrogen bonding. Longer chains are less soluble, and that's due to the extra long non-polar hydrocarbon chain present in those longer chain alcohols. But how do we go about naming alcohols? We'll start with the primary alcohols. So this is a primary alcohol because the OH functional group is attached to a carbon that itself is only attached to one other carbon. Let's name it. Well, this functional group is attached to the first carbon. We have 3 carbons, so it's propan 1-ol. What about a secondary alcohol? This time we're going to attach that OH group to the second carbon. That carbon here is attached to 2 carbons, hence why we have a secondary alcohol. The name of this alcohol is propan 2-ol. And now tertiary alcohols. What you can see true of a tertiary alcohol is the carbon that the functional group is attached to is attached to 3 other carbons. Let's name it. The longest chain has 3 carbons, so it's prop. The alcohol is on the second carbon, so it's propan 2-ol, but we have a methyl group also attached to the second carbon, so it's 2-methyl propan 2-ol. If you have 2 H groups, you have a diol. If there are 3, you have a triol. So let's name this. 3 carbons in a row, so propan, and we have the alcohol functional group on the first and second carbon, so it's propan 1,2-diol due to the presence of the 2 OH groups. Skeletal formulas, I know people find this difficult. In terms of how we go about naming this skeletal formula, notice we've gained another functional group. We've got the alcohol functional group, but we've also got a carboxylic acid. And what happens then is we use hydroxy to represent the alcohol. Count the number of carbons. It's 1, 2, 3, 4. So we have butanoic acid representing that carboxylic acid, and then we have the alcohol functional group present on the third carbon because we're counting in this direction 1, 2, 3. So it's 3-hydroxy butanoic acid. That is difficult. There's 2 methods of producing alcohol you need to be aware of that you'll have met at IGCSE and GCSE most likely. The first one is the hydration of ethene. That means adding water to ethene. Fermentation is your old school approach for making alcohol. So be aware that your raw material for the hydration of ethene is obviously ethene, and this comes from crude oil, which means it's a non-renewable resource. This will run out. As I've already said, ethene is then hydrated. Water is added across the double bond by reacting with steam. We need a catalyst of concentrated phosphoric acid. The reaction is fast, it's continuous, it makes the ethanol continuously, and the ethanol produced is pure. This is in comparison with fermentation. Fermentation uses sugarcane containing glucose as its raw material. Because that sugarcane is grown, we can say that it's a renewable resource. You're going to add yeast because the yeast contains the enzyme zymase, which causes the conversion of glucose into ethanol due to the anaerobic respiration of that yeast. Remember, anaerobic refers to the lack of oxygen. We need an optimum temperature for the enzymes of 35 degrees. As a result of this lower temperature, we're going to have a low rate of reaction. A batch process takes place, and we're going to have an impure product, which we can purify through use of fractional distillation. Let's look at a mechanism for making ethanol through the hydration of ethene. So here's my ethene displayed formula. We've got the presence of H+. Remember, acids such as phosphoric acid, sulfuric acid are H+ donors. So that's where the H plus comes from. It's going to act as an electrophile, which remember is an electron pair acceptor, which is why the curly arrow goes from the double bond to the H plus ion. As I showed you in electrophilic addition, we have the addition of a hydrogen to one of the carbons in the double bond. We have the formation of a carbocation. And then just be careful here, withdrawing the water, which I said was also present in the hydration of ethene. That oxygen molecule is delta negative. This hydrogen here is delta positive. The lone pair on the water attacks the carbocation, another curly arrow. Now, because that oxygen is positively charged, we have the movement of electrons in this bond to the oxygen. I feel like I take up so much space, but here's your final product. As you'd expect in alcohol, it's ethanol due to the 2 carbons, and that H plus is regenerated, hence why it's acting as a catalyst. And then in terms of a high yield, you want a high temperature of 450 degrees Celsius and a high pressure of 75 atmospheres. I'm just going to write the equation for fermentation up here. If you do biology, you'll probably be familiar with it. But we're going to first of all show the formation of glucose by the sugarcane through photosynthesis. So carbon dioxide reacts with water to form glucose, C6H12O6, plus 6 lots of oxygen. And then we take that sugarcane, that glucose, and through the anaerobic respiration of yeast, you produce ethanol plus carbon dioxide. Remember, yeast can be used to make bread dough rise due to the production of carbon dioxide. We must keep that temperature of around 35 degrees Celsius to stop the yeast from denaturing. And then I've stolen this from the revision guide I've written, available on the website SwH Learning. Carbon neutrality. So when the ethanol produced by fermentation is burnt in oxygen, so complete combustion, as you'd expect, carbon dioxide and water is produced. This means that for every 6 moles of carbon dioxide absorbed from the atmosphere by photosynthesis, which remember was responsible for making the glucose, 6 moles of CO2 are released. That's due to 2 moles from anaerobic respiration and 4 from combustion. The use of ethanol as biofuel can therefore be said to be carbon neutral, as there's no net gain of carbon dioxide into the atmosphere. However, we can challenge this due to the various processes involved in planting the sugarcane, harvesting it, transporting it. Often those vehicles involve the burning of fossil fuels, which remember releases carbon dioxide. So it's probably unfair to say that using ethanol as a biofuel is entirely carbon neutral. Now, I've already said that fermentation produces impure ethanol. So how can we purify it? Well, we can use fractional distillation. So here's our impure ethanol containing water. Remember that water has a boiling point of 100 degrees. Whereas ethanol's boiling point is much lower at 78 degrees. So what happens when you heat that round bottom flask is the ethanol vaporizes first, it passes up the fractionating column, and then the water and ethanol are separated in the column because the water condenses back into the flask.